Hello, everyone. My name is 1.4-Kravitz. I'm an assistant professor in the Department of Earth and Atmospheric Sciences at Indiana University. And what I'm going to be talking about is system identification to quantify climate teleconnections. So first, I want to thank the people who helped me out with this work quite a bit. Bethany Sutherland, who honestly did most of the work, Phil Rash and Hai Long Long at PNNL, Doug McMartin at Cornell University, and this work was funded under the HILAT project through RGMA. So we all know what teleconnections are. Here's a great example. This is El Nino. And we know that in an El Nino year, rainfall follows this certain pattern. And similarly with La Nina years, we could make a different map. We could also make maps of temperature. And so teleconnections in general are responsible for many important climate effects, but they're difficult to quantify or even discover. So this map was produced through decades of research. There are many other teleconnections in the climate system, and some of which may not have benefited from decades of research. So the problem with that is, these are really important for predictability on a variety of time scales. So months to a little over a year in this case. There are many others. So what we wanted to figure out is, are there robust systematic ways of identifying teleconnections so that we can sort of come up with maps like these all at once? Is there a way that we can figure out how to do that? So we're using system identification, which is a fancy term for saying a systematic way of perturbing systems to understand how they respond. This is not a new technique. This has been used quite a bit in many other fields. So spread spectrum communication is a great example. This is used in electronics to find faults in circuits on aircraft without actually having to dive in and probe the circuits. And we're using it in climate too. So there are a few ways to perturb a system, and I'm talking about climate models in this case. I'm not talking about real-world perturbations. There are step changes, like the abrupt 4 times CO2 simulation that's part of CMIP. So that tends to put a lot of power into low frequency, so the steady state response. It's not great for looking at high frequency behavior. There are sinusoidal changes where you can perturb, it's how you cram the most power into a particular frequency. And then if you do enough sinusoidal simulations, you can come up with the frequency response of a climate model, as in this study here. So this is temperature response to particular frequencies, and they gathered that by doing a sinusoidal fit to the output and looking at how much did the amplitude change after you pass it through the system. Sinusoidal changes, this is very expensive because you have to do each different period. And then it's also, so another option that we have is broadband changes. And in this particular case, what we did is we took white noise and we low pass filtered it to get rid of some of the high frequency weather variability. And you can add that to the climate model. It sounds silly to add noise to a climate model, but I promise it works. And I'll show you that. And then what you can do is calculate a transfer function, which is based on a cross spectrum. So transfer functions are complex valued. They give you, if you compare, say, the blue line, which is the perturbed run, to a control run, which is the red one, it gives you magnitude, it gives you phase. So that tells you whether the system is amplifying or attenuating the signal. It tells you how long the lag is. And you can also compute the coherence, which is like an R squared in frequency space. So you can combine all of these, you can do some statistical analysis. In this particular example, we found that that shaded region in the top has statistically significant results. And then if you do this on a grid cell by grid cell basis, you can actually start to look at statistically significant responses. So on the left, we highlighted what is the period of the response. So this is the frequency as well. And on the right, we calculated the amplitude ratio. So compared to the control run, how much does the system identification run perturb the system? And you can actually watch signals kind of propagate across. So we identified the PNA propagation westward across the Pacific. I'm sure there are others. So there's a lot more to do, but one of the advantages of this method is it's systematic and agnostic. It provides geographic and temporal information, and although it's preliminary, it seems to work. So we'd love more applications, testing, we'd love to collaborate. I'm sorry I can't be here in person to answer questions, but I'd love to hear from you, so please get in touch. Thank you.